Okay, in this lecture, we're going to talk about what happens when there's more than one source charge and we're trying to calculate the field due to the combined electric fields of those multiple source charges. And it's all about this principle called superposition. Okay, so we're going to read the next section in the book. That's 2.1.3. And the learning objective is to visualize and calculate the vector force due to multiple point charges. Okay, so let's get started. Okay, here I have a bunch of different charges here on the slide. All of the little q's are, again, what we're calling source charges. So now they got numbers because there are 3 of them. But we've got 3 source charges, and then we've got 1 test charge. And again, we're going to use Coulomb's law. We're going to use a vector form of it. And the idea is I want to calculate the force on this test charge due to the combination of electric fields of each of these source charges, okay? And in order to understand how we do this, we have to understand the principle of superposition, which I know you guys have been introduced to before, but this is the idea that fields, electric fields, gravitational fields, magnetic fields, they have no problem being in the same space at the same time. So if I were to throw 2 balls towards each other in the classical sense, right, matter does not occupy 2 different places at the same time. Those balls would bounce off each other, right, because they can't both be at the same place at the same time. Fields, on the other hand, they've got no problem passing through each other. At a single point, if you've got more than one field that reaches that particular point, the resulting electric field will be a superposition of the individual electric fields. Electric fields are a vector, so what you're going to do at that point is you're going to do a vector addition to figure out the magnitude and the direction of our resulting electric field at the point where these multiple electric fields are superimposed. Okay, so superposition really is just this idea that fields from multiple objects are going to be able to fill the same space and either constructively or destructively add together. Okay, so this should be somewhat familiar to you. Again, this would be a very standard problem you might see in introductory physics. And so we can just start by visualizing how this might work. If I wanted to try to figure out the magnitude and the direction of the force on my test charge Q, the one in this one here, okay, I just have to do a vector addition of the individual forces from each of our source charges. Okay, so let's go ahead and draw that out. Okay, so we've got Q2. I'm actually going to make no, it's okay. Q2 has since they're both positive, it's going to exert a force in the downward direction here. I'm going to label that force F sub 2 so we know which source charge it goes with. Okay, our source charge Q3 is going to exert a force that's got about the same magnitude but is in a direction to the right. Okay, and then remember our force vector is going to be in the same direction as that R vector. The R vector between these 2 charges here would be in this direction, so my force vector is also going to be in that direction. It's going to be shorter than the other ones. Again, this is not going to be exact, but because it's further away and the magnitude of the force goes like 1 over the distance squared, it's going to be shorter. If I wanted to figure out the total force due to each of these individual charges, I just need to add the force vectors together. If I did that graphically, visually, mathematically, okay, I would end up with a force vector. Again, this direction is not going to be, or the length is not going to be exactly right. The direction's pretty close to right. Okay, I'm going to end up with a net or a total force, okay, that's going to point down and to the right. Okay, so again, this is what we're trying to do. You guys have done something like this. We're just going to define it in our new terms. All right, so let's go ahead and write out what that would look like in terms of the vector form of Coulomb's law that we just learned about, okay? So this is the force on Q, okay, the total force on Q, and it is equal to the vector addition of, in this case, the force resulting from our 3 source charges, okay? If I were to write out what that looked like in terms of Coulomb's law, okay, I'm going to pull out our common constants here out front, or a common factor. That's probably a factor. I'm going to factor it out. That's a better way to say it. And then I'm going to write out what is left over. Okay, so again, this is the separation vector that we just learned about. This is our unit vector, okay? And I need to do this for 3 of them. Okay, again, you want to be really careful with your notation at this point in your guys' physics career. Okay, I'm being a little bit lazy, and it's okay. I'm not putting the vector signs on the magnitude, the distance squared in the denominator, and that's okay. Okay, but again, let's just recall this part is the vector, that unit vector. This ends up being a scalar. Okay, so that should just be a number that you're dividing each of those terms by. Okay, I can go ahead and draw some of those things here in the picture. So I'm going to put a coordinate system on my picture here. Again, it's just going to be a right-handed coordinate system. And I'm going to go ahead and draw each of those separation vectors. Okay, again, each separation vector is going to be between a particular source charge and our test charge. So this one would be R3. Okay, draw this pretty straight. You want to make sure you get the vectors pointing from the source charge to the test charge. And this guy here. There you go. Okay. And again, that R hat, each of the individual unit vectors are just going to point, for example, I'll draw one of them, right? R script hat here. Each one of those is going to point in the same direction as the associated position vector. All right, so that's for 3. That's for 3 test charges. I want to, of course, be more general than that. So if I wanted to do this for any number of source charges, okay, then I would write that the F on Q is equal to, again, pulling out that common factor. And now I'm going to do a sum from I equals 0, or actually we'll start it at 1. I equals 1 to n of Q sub I divided by our R script here of I squared times our R script hat of I. Okay, so that just simplifies it even more general. Okay, the last thing I want to do here before we move on to the next slide, I'm going to draw our position vectors. Okay, so let's remember our position vectors, they go from the origin to each of our charges. Okay, if they have a prime on them, that means I am going to our source charges. Okay, and this guy, lots of stuff going on with this picture. Nope, that should be a 3. This one's a 2 and prime, and then one more. Sorry for the messy picture here. This one is just R prime. All right, so a little bit more to do here. Okay, I'm gonna actually, just to keep this all on one, You guys might want to move down on your sheet. I wouldn't recommend doing this like I'm doing it up here, but pretend this is just a new part of the whiteboard. Okay, I want you guys to recall from previous lecture that this vector here, our r script hat, our unit vector, is equal to r script divided by the magnitude of r. Some of these things are looking more like you, Muse. Ugh. There we go. And each one of those is going to be r minus r prime over the magnitude of r minus r prime. Okay. So if I go back and look at this particular formula here, okay, I want to look at that. This here is still going to be the same as this. Okay, this is the same as this. The only difference is this denominator is squared. Okay, if I want to substitute in this formula here in for our r hat I here, okay, you end up with this particular equation. Okay, again, from your text, we got our common factors out front. Okay, and then we've got q sub I. I'm going to pull that out here. And then divided by, oh, I need a, yeah, that's good. Minus r sub I prime. Okay, and this is now going to be to the third, all right? So you might be like, oh, I thought it was an inverse square law. Why is this to the third? The third comes from the fact that you're going to get this term squared here, and then when you replace this with this form of r hat here, you're going to get another term in the bottom. That's going to give you the third exponent up here. And then this part here, I forgot a little vector bit. Okay. This part here is a vector. It no longer has a length of 1. Okay, this is the separation vector, but you're normalizing it by having an extra factor of our magnitude of the separation vector down here. Okay, so we want to make sure, take a little bit of time, stare at this, make sure you understand this formula, make sure you understand where this cube comes from, okay? And then I'm going to ask you guys a question. What would this look like in Cartesian coordinates? Okay, so that's basically replacing those r's with some x's and some y's and some z's.